Hello there. Dr. Steele, the instructor for General Chemistry 2 during this fall semester at your College of Pennsylvania. Welcome to your first pre-lab video of the semester. Each week there should be a video prepared that would allow me to introduce to you the concepts and goals of the experiment that we'll be conducting in lab each week, and then to address some of the safety concerns as well as issues with the pre-lab questions. So let's get started with the first experiment of the semester, calorimetry experiments. We've covered the concepts for calorimetry experiments in chapter 6 of our textbook, and so we should be well prepared to accomplish today's goals. Through the experiment today, we'll really do three things. We'll observe three things to get to our ultimate outcome. First, we'll be trying to measure a quantity of heat that is transferred by a reaction that's occurring to its surroundings. And so this would involve being able to measure or calculate heat flow. We've learned two formulas for calculating heat flow in chapter 6 of our textbook. When there is a change in temperature, the heat is quantified as the mass of the system times the heat capacity times the change in temperature. And when there is not a change in temperature, but rather a reaction, the heat quantity transferred is the moles of limiting reactant times the enthalpy of reaction. We'll actually need both of these to accomplish this first goal. We'll set this reaction up inside a calorimeter. So our calorimeter, which is this little device that I have in my hands now, becomes its own little universe, its own little self-contained universe. Inside the calorimeter is simply another cup and then some insulation, which keeps whatever's happening in the calorimeter here from an energy perspective. And all of the energy outside of this in the lab is not able to interact with the contents of the calorimeter. So this becomes its own little universe. We're going to make one little change. This cup is metal, or if you have a calorimeter with a metal cup in it, I want you to remove that and replace it with a glass beaker. Okay? This is a 150 milliliter glass beaker that slides right in there. The reason we need to do that is we're working with acids today, which could react slightly with the aluminum cup, and that would affect the outcome of our experiment. So once we set up our calorimeter and realize that it is its own, again, little universe, the first law of thermodynamics says that the change of energy, the change in energy, total change in energy of the universe, or of our calorimeter, is equal to 0 during any process. And if we look at this statement here, we will have heat being produced by a reaction and a heat change of our surroundings. Okay? We will be able to measure the heat of our surroundings today, because the surroundings will experience a change in temperature. So that means we'll use the first formula that we have up here. And inside the calorimeter, the quote surroundings will be the combination of the acid that we use, which is really just water. So we can estimate the behavior of the acid, or the property of the acids, to be the same as those of water, plus a small amount of solid that gets added to that. Okay? So you'll need to keep that in mind. The reaction is really an invisible thing. It's a reaction occurring at the molecular level inside the liquid contents of the calorimeter, and it's going to produce or absorb energy, which would then go to or be coming from the surroundings. So we will measure the change in temperature of the liquid in our calorimeter to find the heat that is transferred to or from the surroundings. Then we can solve for the heat of the reaction. It will simply be the negative, right, of the Q of the surroundings. When I solve this equation for Q of the reaction, the heat transferred by the reaction is the negative of the heat transferred to the surroundings. Okay. Now this heat, the quantity of heat in this case, is associated with a very small amount of the solid. The first reaction that you'll do, for example, will be, I believe, magnesium metal plus hydrochloric acid, HCl. This will produce MgCl2 and some hydrogen gas, which you'll see bubble out of your solution, out of your calorimeter. Okay? We are going to set the system up so that the magnesium is the limiting reactant. Therefore, this amount of heat is associated with the amount of magnesium that we use. But we would like to convert that or rescale it to the molar level. How much heat would be used per an entire mole of magnesium? We can't afford to use a mole of magnesium in today's experiment. 24 grams per student group would be quite a lot of magnesium. It would be very expensive. Also, the amount of heat generated would be enormous in each of those cases, and it would become unsafe to work with those quantities. So we can work on a much smaller scale with just a gram or a half a gram, for example, and then scale up from there. Now, the scaling up actually is this other formula for heat flow. The delta H of a reaction is the heat of the reaction, heat flow, divided by the moles that were used actually. So you will know how many moles of magnesium you used because you'll have weighed it. This will be the N, you'll convert mass to moles, and then you'll use this value of heat right here to get the delta H of this reaction. Or any reaction, for that matter, that you conduct in your calorimeter. Okay? So that's how we'll accomplish our first two goals. Now the ultimate goal of today's lab is to come up with the enthalpy change, the delta H, for a combustion reaction. You're going to do it for two, but one of them could be Mg plus half a mole of oxygen to form MgO. This is a particularly violent reaction when it occurs and generates a lot of energy. Magnesium is actually often part of fireworks that are made. It produces a very white color when it burns, and so most likely if you see fireworks at any fireworks display, the white color in the fireworks themselves is coming from magnesium metal that is included in the firework that's being launched off. A little side note for you. So we can't study that in our little calorimeter because it would probably be enough energy to melt the calorimeter, even on a small scale. All right? So we're going to use Hess's law to come up with this energy. And remember, Hess's law tells us that if we can add together a group of reactions to give us our target reaction, then we can simply add together the respective enthalpy changes to give us the enthalpy change of the target reaction. One of your pre-lab questions asks you to practice using Hess's law in addition to your practice that you've been doing in class. It says to find delta H reaction for 2 NO2s plus half a mole of O2 to produce N2O5. You're given two other reactions and their associated enthalpy changes. N2O5 decomposes to 2 nitrogen monoxides and 3/2 oxygen. That has a delta H of positive 223.7 kilojoules. And nitrogen monoxide plus half a mole of oxygen produces nitrogen dioxide. This has a delta H of negative 57.1. So using Hess's law, we can flip the first reaction because we want N2O5 to be our product, and we want 1 mole of N2O5 in this target reaction. So 2 NOs plus 3/2 O2 would give us N2O5. Because we've reversed it, the delta H is -1 for the reverse times the 223.7. And then we can look for some cancellation. We're not going to want any NO in our overall process, so we can use this reaction to cancel it. NO's on the wrong side though, so we have to flip this reaction as well. And we need to scale it up times 2 so that we get 2 NOs to cancel out. So the impact here is -2 for the reverse and the doubling times the negative 57.1. When I add these two reactions together, first distribute the coefficient 2. So my 2 NOs will cancel out. 1 mole of oxygen would cancel out, leaving a half a mole of oxygen there. And what drops down? 2 NO2s plus half a mole of oxygen. And on the product side, the product side is N2O5, just like we wanted in our target reaction up here. Therefore, the delta H of this reaction is equal to -223.7 plus -2 times the negative 57.1, or -109.5 kilojoules. This is pre-lab question 3, so we've covered that one for you, and you should have no problem with that now. The other 2 pre-lab questions make use of these equations that I'm erasing right now. Let's look at them briefly. Again, we've done examples of this in class, so this should be no problem. The first question says to calculate the heat absorbed by 34 grams of water that increases its temperature by 7.25. So when there is a temperature change, the heat transferred, or heat flow, is mass times heat capacity times change in temperature. So 34.0 grams of water times 4.184 joules per gram degrees Celsius and 7.25 degrees Celsius. So the heat absorbed is 1,030 joules, or 1.03 kilojoules. Okay? Again, that was absorbed by the water, by the surroundings. In today's lab, that'll be the sort of the first step. You'll see what happens to the surroundings, which again will be essentially water. So you'll be doing this, pretty much this exact calculation. This heat then came from a reaction, so then that's why we would put a negative sign on it for the Q of the reaction in today's lab. Okay? Question 2 in the pre-lab is related to calculating the sort of the molar quantity of heat on a mole scale. We need to convert the 4.50 grams of ammonium nitrate, NH4NO3, to moles. The molar mass of NH4NO3 is 80.05 grams. So we have 0.0562 moles. When this was dissolved in water, the heat change, it says, the Q, was 1.445 kilojoules. That was the heat for this amount of ammonium nitrate. But we're asked to calculate the molar enthalpy. So on a mole basis, the delta H enthalpy of solution, in this case, instead of a reaction, it's a solution, is going to be the heat divided by the moles. So 1.445 kilojoules divided by 0.0562 moles is 25.7 kilojoules per mole. That's the enthalpy of solution. In today's lab, you'll basically use the heat from a calculation like this to be the Q in this numerator, and then the moles would be your limiting reactant. Again, most likely your solid, your magnesium in the first example. Okay. And you're going to work with a couple of different reactions, as I said, magnesium and magnesium oxide, and then another different metal and its oxide to compare how much energy is involved in each of their formation reactions that you'll be looking at. Okay. You will be working with acid, and it's fairly concentrated so that we get rapid reaction in today's experiment. So take care when you're handling the acid. Avoid spilling it on your hands and on your clothing. You may want to wear a lab apron. Not really necessary as long as you're taking the appropriate precautions not to spill the acid. And you might want to wear gloves as well if you have sensitive skin. The acid is not strong enough to directly burn you as soon as it gets on your hands, but this is always a personal issue. Everyone's skin has a different sensitivity to acid. So if you're worried, you might find yourself wanting to wear a set of a pair of gloves in today's laboratory. As always, if you do get any acid or any chemical on your skin, you would want to immediately proceed to the sink and copiously rinse your hand or the affected area with water for a couple of minutes to clean that area, and seek your instructor's help if anything should happen. Other safety concerns or notes that I would like you to be aware of today: don't be alarmed if when you're doing your experiment you see gas coming out of your calorimeter. That's one of the products of the chemical reaction. So don't overreact or anything. Okay? You'll be measuring the temperature of your setup today with a digital thermometer. There is a hole in the top of the calorimeter for you to simply put the thermometer in there. A lot of times students try to use some type of a clamp and just set up the system like this to let itself go, and you simply have to read the thermometer throughout the experiment. All right. This will be placed atop a stir plate. Keep in mind that our stir plates in the lab are both stir plates and hot plates. So place a magnetic stir bar inside the calorimeter setup and then put it on top of your stir plate. Please be extra cautious that you are only turning on the stirring component of your stir plate. We have had students and myself be burned in the past when people have turned on the heat function and they're not paying attention in the laboratory. This ruins the entire experiment, in addition to being a safety hazard, because if someone doesn't know this is hot and they grab it, that's how they'll get burned. And also, while this is insulated, it can't overcome a hot plate just cranking energy into it from the bottom. And so if you have the hot plate on, you'll certainly be violating sort of the first law of thermodynamics for the interior contents of this experiment. Pay attention to the waste that's being generated in today's lab. It is acidic, and it does contain metal ions in some cases, or salts, I should say, of those metals. So we are not going to pour it down the drain. There are waste collection containers in the waste hood. There may be a variety of containers in those hoods, so please read the labels correctly. I could direct you to some news articles, unfortunately, that have appeared in just the last year or two, where students in chemistry labs at other colleges and universities have inadvertently disposed of their waste in the wrong container and been harmed because of an explosive reaction that occurred immediately when the waste was put into the container. So it's a serious concern how you dispose of your waste, and be sure that you read a label before you dump the contents into the bottle, particularly with acids and bases. We want a safe, good experiment today that really reinforces the concepts of calorimetry and Hess's law, and we don't want any accidents to take place. Also, as part of today's lab, you'll be getting a brief tour of the laboratory if you're new to this facility because you're a transfer student or a first-year student. So we'll run you through that, and we'll take a safety examination before we get started. But beyond that, I've highlighted the major points of the experiment, and I think you should be all set to go. So make sure you have a good day in the lab. Ask questions of your instructor and the student assistant who may be available, and we'll be happy to help you out as best as we can. Have a great day.